Hi there. In this video, I will be discussing about system modeling. There are two objectives in this video. The first is to be able to establish the mathematical model of physical systems using mechanical model. And the second is to convert the mathematical model equation into transfer function. There are two types of modeling systems. The first is mechanical model and the second is the electrical model. In this video, I will be discussing about the first model or the mechanical model. So first, let's start defining some terms and variables. The variable f of t represents the force in the time domain, and it will be the stimulus to the system. And this is referred to as the input to a mechanical system. X of t, on the other hand, is displacement, which will be the response of the system, and it will always be the displacement again in a mechanical system. X of t is a linearly independent motion. There can be one motion or several linearly independent motion in a mechanical system. We will be using Newton's second law to analyze and derive the equations of the input and the output variables. So Newton's second law states that the relationship between an object's mass m, its acceleration a, and the applied force F is just F equals ma. If there are several forces, then this will be the net force acting on the mass m. We will be using three components to model mechanical systems. So the first component is a spring. Spring will be defined by its spring constant K, which has a unit of newtons per meter, and the spring can either extend or compress depending on the force applied to it. The second component is a viscous damper, and it is defined by its damper factor B. The damper factor B is in Newton's second per meter. The difference between the spring and the damper is the spring stores energy, and therefore at any point in time it will release this energy, while a damper dissipates the energy, converts the energy into heat, and therefore we can no longer retrieve back the energy. The third component we will be using is a mass with the unit kilogram. Let's talk about these three components and their reaction forces. So if we have a spring, it will have a spring reaction force. We will denote that by Fk, K for the spring. This force is just equal to the spring constant, K, and its displacement or deformation. In this model, we will be assuming that the spring is ideal, meaning when the energy is stored in the spring, this energy will be conserved and it will not be wasted. Hence, the spring will be oscillating infinitely. The next component will have a reaction force. We call it the damping force, denoted by B, Fb. And damping force will just be equal to the damping factor B times the velocity, which we know is equal to the first derivative of displacement with respect to time. So V represents velocity and X of t represents displacement. The third component is the mass, and it will exhibit an inertial force. This inertial force is due to the inertial mass. So this inertial force is just equal to the mass times its acceleration. If a force is applied to this mass, then this mass will move in the direction as the force, and it will also have a velocity in that same direction. So the mass times the acceleration is the inertial force, which is also equal to the acceleration. As we know, is the first derivative of velocity with respect to time, and velocity is the first derivative of displacement with respect to time. So acceleration will be the second derivative of the displacement with respect to time. Let us now summarize the three components. We have the spring reaction force is equal to K times displacement xt. Converting this into its Laplace, we have f of s equals K times x of s. If we will introduce a variable which is referred to as impedance in this modeling, Z, it will be equal to the force divided by the displacement in Laplace. So if we have the force divided by the displacement, then the impedance of a spring will just be equal to K. The second component is the viscous damper. So the force of reaction of a damper will just be the damping factor B times the first derivative of the displacement with respect to time, converting it into its Laplace. We have this, and if we get the impedance, which is Fs divided by x of s, then the impedance of a viscous damper will be B times S. And the third component, which is the mass, will have an inertial force equal to the mass times the second derivative of the displacement, and this will be its corresponding Laplace transform, and the impedance will be ms raised to 2. Okay, let us illustrate this with an example. This example is a 1 degree of freedom example. Obtain the mathematical model equation of the system shown below. So we have a mechanical model below, and then we will convert the model equation to Laplace transform, and from this Laplace transform we will determine the transfer function. We have one mass here connected with a spring and a damper over a wall, which will be referred to as our references. This will be rigid and they will not be moving. In this problem, it is also stated that the surface, the mass and the surface will not produce any friction. So we will not consider friction in this example. A force has been applied in this direction towards the right, and therefore the mass will move in that same direction, denoted by x of t. And the spring will extend in this scenario. So the force of reaction of the spring will be against the direction of the force going to the left, as well as the damper will resist the applied force. So we can see the forces when we will have our free body diagram. So the analysis of mechanical models starts with the free body diagram. Free body diagram represents the forces acting on a mass or a body. So in this example, we have the force. So this is the force going to the right. And how many reaction forces do we have? We have the damper. This is the force of reaction of the damper. And this is the force of reaction of the spring. They are opposing the applied force. And the displacement, of course, is in the same direction as the applied force. So using Newton's second law of motion, the summation of forces, or the net forces, will be equal to the inertial force, mass times acceleration. So to get these net forces, it will be equal to F of T. This will be minus, so minus the reaction force of the damper minus the reaction force of the spring will be equal to mass times acceleration, which we know is the second derivative of the displacement with respect to time. And putting all this negative to the right side will make these two terms positive. Therefore, rearranging it, we will have this as our model equation, or we call it the differential equation. So looking back, so this is our differential equation or the model equation of the mechanical model. This is the mass, second derivative of the displacement, plus the damper, first derivative of the displacement, plus the spring times the displacement. It will be equal to the applied force. Now, if we are going to convert this into its Laplace transform, then x double prime will be s squared, and x of t will be x of s. Same is true with this term. First, x prime will have s, and k x of t will have a Laplace transform of k x of s, and this is equal to f of s. Remember that when we get the transfer function, converting this model equation into its Laplace transform, we always assume that the initial conditions are set to 0. If we factor x of s in all these terms, we will have x of x times this quantity from the mass, from the damper, and from the spring, and it is equal to f of s. Remember that all of these terms are the impedances of mass, the impedance of a damper, and the impedance of a spring. And to determine the transfer function, which is g of s, and which is simply equal to the ratio of the output and the input in Laplace transform, then it will just be doing our algebra. We will have 1 all over the mass s squared plus the damper constant s plus k. And to illustrate this in a block diagram, this represents our input f of s, this represents our output x of s, and the mathematical relationship that coins the output and the input is called the transfer function. If in the example we were given the value of the mass, the damper, and the spring, then you simply substitute these values in this equation.